Okay, so what we're going to talk about today is we are going to talk about measurements. Now, here's the thing. You have math class, blah, 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 math class, blah. Now, math class is meaningless. Ooh. So anyway, because the numbers that you find, x equals 3 what? Okay, well, we're going to talk in science, in chemistry, we're going to talk about measurements, not just numbers. Okay, so measurements consist of two things. The first thing that a measurement consists of is a value, okay, a quantity. The second thing that measurements consist of is a unit, okay? Now, a unit tells you what that quantity is, okay? Just saying 3 doesn't tell me what you have 3 of. You need to say, do you have 3 eggs, or it's 3 meters, or 3 something, okay? You need a unit. Otherwise, it's a meaningless number, okay? A measurement is meaningless if it doesn't have units, all right? And meaningless numbers, if you put it on a paper, it's going to lose points because meaningless numbers are just that, they're meaningless. So take a look at this video. NASA learned the hard way that units are really, really important.
The Mars Climate Orbiter launched on December 11, 1998 on a mission to orbit Mars. This first interplanetary weather satellite was designed to gather data on Mars's climate and also serve as a relay station for the Mars Polar Lander, a mission that launched a few weeks later. But you can't just launch a spacecraft towards Mars and trust that it's going to get where it's going. You have to monitor its progress. Many spacecraft have reaction wheels to keep them oriented properly, and navigation teams behind interplanetary spacecraft that constantly monitor the angular momentum and adjust trajectory to make sure it gets exactly where it needs to go. In the case of the Mars Climate Orbiter, monitoring its trajectory and angular momentum involved a few steps. First, data from the spacecraft was transferred to the ground by telemetry. There, it was processed by a software program and stored in an angular momentum desaturation file. That processed data was what scientists used to adjust the trajectory, adjustments that were made by firing the spacecraft's thrusters. Every time the thrusters were fired, the resulting change in velocity was measured twice, once by a software program on the spacecraft and once by a software program on the ground. And here's where the problem comes in. It turned out that the two systems, the processing software on the spacecraft and the software on the ground, were using two different units of measurements. The software on the spacecraft measured impulse, or the changes by thrusters, in newton seconds, a commonly accepted metric unit of measurement, while the processing software on the ground used the imperial pound seconds. And it was unfortunately the ground computer's data that scientists used to update the spacecraft's trajectory. And because 1 pound of force is equal to 4.45 newtons, every adjustment was off by a factor of 4.45. For a spacecraft traveling tens of millions of miles to a destination, a number of seemingly small errors really add up. During the Mars Climate Orbiter's 9-month cruise to Mars, 7 errors were introduced into its trajectory that meant that when it reached the red planet, it was 105 miles closer to the Martian surface than expected. This turned out to be an unsurvivably low altitude for its Mars encounter. When the spacecraft fired its main engine for the orbit insertion burn that was designed to put it into an elliptical orbit, nothing happened. NASA lost contact quite abruptly with the spacecraft. So while we know the root cause of just what went wrong, we'll never know exactly what happened to the Mars Climate Orbiter.
So every measurement has a unit. Every measurement also has some amount of uncertainty to it, okay? For instance, this ruler that you see here on the screen, okay, is marked to the 10th of a centimeter, or the millimeter, okay? Well, we can't measure something to the, 14th decimal place of a centimeter because you can't see it, all right? So what we have to do is we have to figure out what the limit of measurement is for any given measuring device, because every measuring device has a limit of uncertainty, okay? The way that we do that is we say that what you're going to do is you're going to take your measuring device, whether it's a ruler or a balance measuring mass or a graduated cylinder, measuring volume, whatever, you're going to take whatever that smallest value is that you can read, and you're going to estimate one place beyond that. So if a graduated cylinder measures to the nearest milliliter, you're going to estimate to the nearest tenth of a milliliter. Okay? If a balance measures to the nearest gram, you're going to measure to the tenth of a gram. If it measures to the nearest tenth of a gram, you're going to measure to the hundredth of a gram. One place beyond what you can read. Okay? So, for instance, this pencil here, all right, if you look at this pencil, we can see that it's in between 23.6 and 23.7 centimeters. So what we do then is we estimate, okay? We're going to estimate that that's about 20, and it's not quite halfway, so we're going to estimate that that's 23.62 centimeters. Now, is it exactly 23.62? Probably not. It's an estimate, okay? But as you do this more, you can estimate these numbers better, okay? But you're always going to estimate one digit in any measurement. And then you're going to put a unit on it so that it means something.